Assalamualaikum and good day everyone. My name is Dr. Johanna. So today I'm going to explain about the second topic in advanced data structure and algorithm, which is algorithm complexity analysis. So these are the objective of this topic. At the end of the class, we hope that all the students know how to measure the algorithm efficiency and know the meaning of the big O notation. Okay, when we talk about the algorithm analysis, it's about to study the efficiency of algorithms when the input size become grow based on the number of steps and the amount of computed time and space. So basically, in this topic, we are going to learn how are we going to calculate the efficiency of the algorithm by calculating the number of steps, okay, that we have for these certain codes. And we can see that as long as the input size is grow, definitely the efficiency, the algorithm will be more complex. If you're talking about what is an efficient algorithm, okay, in software engineering itself, we know that basically we have a measurements like how are we going to evaluate the effectiveness, the efficiency, all right? So when we talk about this efficient algorithm, it's a measure field which is provide tools for evaluating the efficiency of different solution. Okay, as we know, as we mentioned during the first class, basically when we talk about algorithm, mainly the purpose of the algorithm is to solve a problems. Okay, so basically the algorithm help to solve a problem. It's like a problem solving. All right, so and if we are talking about the computational complexity, it means that we are going to compare the efficiency of algorithms, okay, by measuring the degree of difficulty of an algorithm. Okay, so that is the computational complexity. All right, so when we talk about the complexity analysis, okay, I think the first class we have learned that the complexity can be based on many factor. Okay, it can be because of the domain factor, it can be because of the communication between the stakeholder and the developer, it also can be based on how we solve the problems. Okay, meaning that from the problems, okay, we derive a solution. So basically the solutions, how complex the solutions that we provide. Okay, so when we talk about the complexity analysis, it's actually analysis of effort, okay, whereby it's needed to apply an algorithms, okay, or how costly it is, okay, and it's referring to cost definitely. So that's why we have function points, okay, that is purposely to calculate the complexity analysis. All right, for we have here two examples of the cost measurement. All right, so the first one is faster is better. Okay, so this is referring to the time, meaning that we measure it in terms of time, okay, based on the time that we have. Okay, so it's like, how do you measure time? How are you going to measure by time? The wall clock or the computer clock. And the second one, if we are talking about the cost measurement, we are talking about the space. All right, so less space demanding is better. Okay, but if you need to get data out of memory, so it will take time, right? Okay, sometimes the codes, the algorithm that we provide, okay, will influence the performance, all right, the system to reach the server to give response to the user. Okay, all right, so the algorithm analysis should be independent. Okay, so meaning that if we are talking about the algorithm analysis, meaning that we can implement it, okay, either in any programming language. Okay, we can use Pascal, C, C++, and Java. All right, so basically same goes lah. We can actually also running into specific computers. Okay, and also it will involve a particular set of data. Okay, so we can have string, integer, float. Okay, but size of data should matter. Okay, so basically, if we are talking about the algorithm, it will reflect the size of the data that we use, the problems that actually we want to solve. All right. All right. So basically, the all right, so let's look at this example. Okay, so in this example figure, you can see that here we have n, fn, and squared, okay, 100n, log n base 10, 1000, okay, and here we also have the n, okay, so meaning that it can see that the growth rate of all terms of functions, so meaning that this is the size. So it will increase, and you can see that the growth rate is also increase. Okay. All right. So if you're talking about the analysis of algorithm, okay, so basically there are three possible states, okay, which is referring to the algorithm analysis. Okay. The first one is known as best case. Second is average case, and the third one is worst case. Okay. And the worst case is always considered, meaning that it's the maximum bond rate, all right, for the execution time or memory space, okay, for the any input size, okay, because just now we are talking about the efficiency, the cost measurement, all right, we evaluate based on two, right, time and space. And the execution time for the worst case is the complexity time, okay, so this is the complexity time, right? Later we are going to see how, okay, based on which codes, okay, how are we going to categorize these codes. This belongs to base case, this data set is belongs to best case, this data set is belong to average case, okay, later we're going to see. All right, now what does it mean by the worst case efficiency, the best case efficiency, and the average case efficiency? Okay, so the worst case efficiency, actually it takes longest running time, okay, longest running time. If we are talking about the best case, then it is actually the shortest running time, okay, and if we are talking about the average running time, okay, for example, as a very simple example, if let's say here I have an data size here, okay, if let's say I start with the index of the 0, 1, 2, and 3, okay, assume that I have three set, I have A, I have B, okay, and I also have C data set here. All right, okay, now let me draw 1, 2, 3, 4. Okay, all right, so here we can have 0, 1, 2, 3. Here also we have 0, 1, 2, 3. Now if we are looking at three data set here, if let's say my first data set, okay, the value is 1, 2, 3, 4. All right, and if let's say for the B, let's say I have here 2, 1, 3, 4. Well, the data set here, I have 4, 3, maybe 4, 2, 1, and 3. Now, by looking at the value of the data, each of the data set is whole. Okay, now let's look at the first data set here. If you're talking about, if let's say the instruction is that please sorting, okay, the value, okay, in ascending order. So basically you can see that, okay, you can see here for the data set A here, I have already, the data here is already in sorted order, okay, meaning that we don't have to put much effort on that because it is in sorted order already. So in this case, okay, just imagine if we are talking about the sorting process, okay, since this is already in sorted order, so meaning that this one, it can be categorized under the base case efficiency. All right, now looking at the B data set here, the second data set here, I have 2, 1, 3, 4. Okay, So basically, I just need to compare and swap for this part only. Okay. So maybe this one maybe took about 5 seconds. So maybe this one around 10 seconds. Okay. So these can be categorized under the average case. Now, looking at the third data set that I have. So in this data set, we can see that, okay, it's random. It starts from 4, okay, and it's end with the value of 3. Okay, so meaning that here in this, with this data set, meaning that it took a lot of time for me to sort it, okay, because it starts with the largest value, okay, and the last value is the medium value. All right, so we can know that this data set can be categorized as the worst case efficiency, okay, because it will take longest time. The best case is shortest time because it's already in sorted order, right? All right. As an example, okay, just now I mentioned to you some of the example based on the data set, right? So basically here we can see that, okay, for the best case here, we get lucky and find the target in the first place, okay? CN1, okay, meaning that we just go directly. If let's say just now my example is that the first in that here I have A, right? So maybe if the instruction is that, okay, please go to the index of the 0, okay, is it the value of the index 0 is equal to A? Yes, so that definitely it will be 1, all right? For the worst case, meaning that we have to look at every element, okay, meaning that in other words we have to traverse from one index to another, okay, until we find the value that we want to search for, okay. So this would be N, the complexity, because we have traversed from one element to another until we find it, okay. How about the average? Okay, this one depends on the probability, okay, the probability that will the target will be found lah, okay. So the complexity time, actually it can be presented by the big O notation, okay. So the big O notation should be right like this, okay. So this is O and this ACC is actually referring to the class of the algorithm complexity, okay, meaning that this is the class complexity. So the class complexity, we have few class complexity, okay, and it start from 1 and so on. Now looking at this one, okay, the notation that used to show the complexity time of algorithm. So basically here we have class complexity, okay. In the class complexity, you can see that we start from the O1, okay, meaning that it's constant, finding the first element in the list, okay, like the previous example that I've shared with you, right? We are looking for value A, okay, and since we start from here, so basically we can search it. All right, now the second one is log-n base X. All right, so the log-n base X is actually problem complexity will be increases slowly, okay, as the problem size increases, okay, meaning that the complexity actually will increase depending on the problem size. So when the problem size increase, then the complexity will be increased. All right, so squaring the problem size only doubles the time, okay. So that's why we can conclude that is log-n base X. Later we'll see example which codes we're referring to the log-n base X complexity. Now, if you're talking about the ON, I think this is very simple and very easy to understand, okay? Because we can see, as I mentioned before, the moment that we need to traverse from one index to another, so basically the complexity would be N, all right? Because, for example, we counting the elements in a list, okay? So this is ON. Next one, we have ON log-n base X. All right, so this one is referring to the log linear increase. Okay, so just now we say that the problem complexity increases a little faster than N. Okay, so the characteristic whereby we are going to divide the problem into the subproblems, okay, that are solved the same way. For example, later we're going to learn about the merge sort, okay. Then for O n squared, okay, it's quadratic increase, okay. So the problem complexity increases fairly fast, okay, but still manageable, okay. And the characteristic is that we have two nested loops of size n. If you still remember, we have On here, right, before this. All right, if On meaning that we count, okay, until we reach the last element in the list. Now, if let's say we mention about the n squared, meaning that we have two nested loop. If On, we have one for loop. For the n squared, we have two nested loop. While for the On cube, we are going to practical for more emphasize lah. Okay, so this will be cubic increase. All right, and the most complex is actually O to the power of n, which is exponential increase. So it increased too rapidly, okay, to be practical. So meaning that the problem complexity increases very fast, okay, the value increases very fast, okay, and definitely when the problem size increase, the complexity will be increased. Now, let's look at this example, okay? In this table, you can see that, okay? Now, this is the comparison graph, right? So, this one, you can see that these are the function, which is the complexity class, okay? The complexity class of big notation. And here, we can see this is the n. N is referring to the problem size. All right, so you can see, let's look at the first one, which is O1, the complexity 1. So you can see that no matter, okay, no matter the size of the data, 10, 100, right? So meaning that the size increase, right? But the value will remain 1, okay? And when you see log n base 2, you can see that it will increase. Same goes to the n. Same goes to the n times log n 2, log n base 2. This is n log n base 2, okay? But you can see that for the 2 to the power of n complexity, the value will be increased more, okay? So that's why we mentioned that, okay, increases very fast compared to the other class complexity, all right? Now, let's look at, all right, so these are actually, just now we've learned about the class complexity, all right? We have the class complexity, right? Okay, so in this part, we're going to look at, here we have a code and here is a notation class. We are going to look at if these lines of codes, then it will referring to which class complexity, all right? All right, now let's look at the first one. We have a 1, which is constant. Okay, so you can see here that by for the lines of code whereby we initialize the value or we just print out, so the notation would be O1 direct, right? Now let's look at the O locand base x here. Okay, so for the locand base x here, the keyword is that, okay, this is base x, right? So basically, when we want to calculate the number of steps, okay, and we want to categorize it belongs to which notation, right? So the first thing is that we must to look at the for statement here, okay? So in this for statement here, we must check the I value, all right, is initial to what value, and then the condition here, and also how it increase, all right, how the I value is increased. So basically, if the I is increased by multiply the I with the value of x, so it will be log n base x, okay, as long as the x I here is equal to x, all right? Let's look at this one, the ON. Okay, for the ON, it's very simple. Like I told you just now, if we are talking about the log, we are talking about the complexity is n, meaning that we are going to traverse from the first index up to the next index until we reach the end, the last index in the array, okay, in the data set, in the list, all right? So here we can see that for the ON, right? So you can see that, assume here for this example, let me try to erase first, okay? For this example, you can see, okay, let's say we start from the 0, okay, because we are supposed to start from 1, okay? So here I'm going to have 1 because here the I is equal to 1. So we are going to start with the index 1, all right? So you can see here that, all right, the I is plus plus, meaning that the I value will increase 1. Okay, if let's say we have here 1, 2, 3, 4, so the I here would be 4, right? So the I value will increase by 1. So meaning that we are going to plus 1, and so on. All right. So in this case, okay, because the I is increased by 1, so the complexity class would be, the notation would be ON. Okay. Now, let's look at n log n base x. Okay. You remember, if we are talking about the n, meaning that we have log. Okay. But in this case, the I value is increased by time with x, whereby just now I told you, if the I is increased, okay, by multiply the I with the x, right? So we're going to have log n base x, okay? But since we have n here, so it will be n log n base x, because basically we are going to times the notation of these lines with the notation of this line. Then we get n log n base x. Okay? Okay? Okay, this one is very simple, okay? Because we're going to have 2 for loop, right? So we can have here n, this one also n. So when n times n, it will be n squared, all right? Same goes to this n cube, okay? Meaning that we're going to have 1n, second n, third n. So that's why the complexity will be n cubed. And you can see that each of the loops, all right, the incremental value is increased by 1, plus, 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 okay? The last one here is O to the power of n. So basically, when O to the power of n, you can see that we have 2, 1 while and 1 for loop, right? And basically, you can see that the second 4 here, okay, the condition here, the J here is depending on the first loop. Okay, is depending on the value of the first loop. All right, so that one we categorize it as O to the power of n. Okay, we'll meet in the second in the part 2 later. Bye bye.